part of your
Okay.
lectures.
Okay, I am trying to record.
Only presentation.
Yeah. So okay, we have started slightly later, but well, I will try to make this lecture accessible to all possible audience. From what I know, the audience consists of different people, starting from first-year students to PhD students, and even some adults who pretend to be students, which is, of course, appreciated. But I mean, I'm trying to be accessible for all, at least in the first lecture, which was very popular, and the second one, which is not that popular, but more elaborated, but nearly as advanced as the last lecture of Yaroslav, of course. So I will repeat basics about groups and come to the representation theory in this way. So from what we know, a group is a set together with a binary operation, which is associative. So the product is associative. We can put the brackets in two possible ways, and the result is the same. And there exists a neutral element, the identity, such that the left and right multiplication with respect to this element does not change another element. I put this A, but in fact D. And for each G, there exists an inverse, which is also there. It will be unique, such that G with G inverse equals to G inverse times G equals to the identity, the neutral element. So there are more general notations like a semigroup, which is an algebraic structure consisting of a set together with an associative binary operation. And this is precisely the first property. If there exists a neutral element, it is unique. And then the semigroup is called a monoid. This is the second one, the second property. So the first two are satisfied, it's a monoid. And if all three are satisfied, then first of all, the inverse is always unique. And then a group is a monoid with all inverses. So this is the tower of different objects. In fact, all of them are important. So let me give examples, and today's lecture will consist of a lot of examples. So first of all, non-zero real complex or rational numbers with respect to usual multiplication of numbers. Second, symmetries of some system with respect to the composition of transformations. All bijections, which are called automorphisms of a set X with respect to the composition. Sometimes it's called a symmetric group of a set X. The general linear group GLV of a vector space V, the vector space is over some field K, in our case it's usually R or C, and this consists of all invertible linear maps from V to V. And again, the multiplication is the composition. A group is called commutative or abelian if the multiplication is commutative. So it does not depend, so the product does not depend on the order of elements. G1, G2 equals to G2, G1 for all G1, G2 from G capital. For example, 1 is commutative, always commutative, so numbers with respect to the usual multiplication. 3 and 4 are generally not commutative, but if X consists of one element, of two elements, the symmetric group or automorphism group of X is still commutative. And if the dimension is equals to 1, then the general linear group is just given by multiplication by non-zero numbers. And this is again an example 1, so it's commutative. A subgroup is a subset AH of G, which is closed under the group multiplication and taken of inverses. So if it's closed under multiplication and taken of inverses, then it automatically contains the neutral element. So it's a group itself. A subgroup is called normal if it is stable under the conjugation. So for any element G from G capital and H from H capital, GH, G inverse, which is called the conjugation of H by G, belongs to H capital again. So it's another element from H capital. Given a subgroup H of G, we can define the following relation. We say that G and G2 are related, so it's a binary relation. If there exists some element H small from H capital such that G1 equals to G2 times H. In fact, we can write also H times G2. And for an arbitrary group, this will be an equivalence relation, but the two equivalence relations are different. So we can prove that this is an equivalence relation. It's reflexive, symmetric, and transitive. And the set of equivalence classes with respect to the above relation is the quotient of G by H, and it's denoted as G over H. And then it's a natural question whether this quotient is a group itself, and it's true if H is a normal subgroup, sorry. Then G over H is a group with respect to the operations. The equivalence class of G times the equivalence class of G2 equals to the equivalence class of G1, G2. And the equivalence class of G inverse is the equivalence of class of G inverse. And the result does not depend on the choice of representatives, because we can take different G1 and G2 in the same classes. They're different by multiplication on some H. But the result, if H is normal, the result will be the same. This is the property of the normality property of H. And the neutral element in G over H is the class of the neutral element in G. So let me give examples of subgroups. So for instance, non-zero rational numbers inside which are denoted Q star, inside non-zero real numbers R star, and non-zero real numbers R star inside non-zero complex numbers C star are normal subgroups. In fact, a subgroup, yeah, I will say they're normal, they're subgroups. And in fact, if you have subgroup of some group, and this group itself is subgroup in another bigger group, then the smaller the subgroup of the biggest one. So a subgroup of a subgroup is a subgroup. It's just easy to see. All the subgroups are normal because any subgroup of a commutative group is normal. Indeed, if you look at the definition of conjugation, then if the multiplication is commutative, then GH, G inverse is the same as G inverse H is the same as H. So it's always does not change H. For that reason, it's always an H capital. So if the group is normal, if the group is abelian or commutative, then every subgroup is normal. Another example of a subgroup is symmetries of some system inside all bijections. In particular, if you take all non-degenerate invertible linear transformations of V, of a vector space V, then apparently it's a obviously it's a subgroup of the group of all bijections of V. Now we can specify linear transformation by requiring that the determinant equals to 0, and we can always define the determinant if the vector space is finite dimensional. And then so we know that determinant is a multiplicative operation. So the determinant of the product of matrices is the product of determinants. So if two matrices have the unit determinant, then the product will satisfy the same property. It means, and the same for the inverse. It means that all matrices, all linear, invertible linear operators with the unit determinant will be inside GLV, will constitute a subgroup. This subgroup in general is not normal, of course. So sorry, this subgroup is normal indeed. So this you can see that. I mean, it's not abelian; it's normal. Of course, you can see at the definition of the conjugation. If you take H with the determinant equals to 1 and an arbitrary linear transformation G, and they take the determinant of the conjugation, it will equal to the determinant of G times the determinant of H times the determinant of G inverse. But the determinant of G inverse is the same as the determinant of G inverse. And then it will be cancelled, and only the determinant of H will remain. And this is 1. So it will be still in the same SLV. So the group center Z of G, let's take an arbitrary group G and consider the set of elements G inside G capital, which commute with all elements in G. This is called the group center of G. And this is a normal abelian subgroup. Yeah, the conjugation will not change elements from Z to G, just if you look again, definition of the conjugation. And if you take the subgroup which consists of identity minus identity, or 1 minus 1, inside GLV, it's again a normal subgroup. And in fact, if the dimension of V is greater than 1, this normal subgroup is indeed the center. So it's the previous example. Now, whenever we know some algebraic objects, algebraic structures, we are always interested in maps which preserve these structures. In the case of groups, these are morphisms of groups. So a morphism of two groups, phi from G1 to G2, is a map from G1 to G2 as sets such that phi of G1, G2 equals to the product of phi G1, phi G2 inside another group G2, and phi of G inverse equals to phi G inverse. From these two properties, it's easy to see that phi of E of the neutral element equals to the neutral element in another group. The kernel of a morphism of two groups, phi, which is the set of G and G1, it should be G1, such that phi of G equals to the neutral element, is a normal subgroup of G1, while the image of phi is just a subgroup of G2. So you see, if you take two elements, if just easy to see if you never did this exercise, just an easy exercise. A morphism of groups is called a monomorphism, epimorphism, or an isomorphism if it is injective, surjective, or bijective as a map, respectively. Let's take a group morphism phi from G1 to G2. Then, as I said before, the kernel of phi is a normal subgroup inside G1. So we can take the quotient of G1 by this normal subgroup. It will be a group. And you can see that phi induces a map from G1 divided by the kernel of phi to G2. Simply we take the class of an element in this quotient, apply phi to this to any representative, and we'll see that phi of this phi applied to this representative does not depend on the choice of representative, simply because two representatives are different by some element in the kernel of phi, which goes to the neutral element. So we can so it means that phi, a morphism of group, induces the canonical map from the quotient group G1 by the kernel of phi to G2. And this is a monomorphism, because actually we already killed all possible kernel. So the kernel is inside kernel phi, but we also quotient out by this. So this is a monomorphism. If you take G1, then the image of G1 is again a subgroup in G2. And we can say that phi induces a map from G1 to the image of phi. And this is an epimorphism, because every element in the image of phi is the image of some element in G1, which means that the map is surjective. And if we take now the map from G1, combine both and take the map from G1 over the kernel of phi to the image of phi, it's an isomorphism. The composition of two morphisms of groups is again a morphism of groups. So because it will respect all the algebraic properties. The inverse of an isomorphism is again an isomorphism. So it means that if you take morphisms of groups as maps, then this subspace will be closed with respect to the composition and taking the inverses. It means that morphisms will be, again, morphisms of groups will be some algebraic structure. And I will say what kind of structure. So a category is a category. So a category is a collection of objects that are linked by some arrows. To be more precise, a category C consists of a class of objects, which are denoted as objects ob C. So these are objects, or you can visualize this if the category consists of finite or discrete, or at least visualizable set of not class, but set of objects. Then we can view this as points, and then a class of homomorphisms between two objects we can view as arrows. So if it's finite or discrete, this kind of graph, in fact. So and then we should have also the composition of morphisms. We take one morphism which goes from A to B, and another one which goes from B to C, then we can compose and get something which goes from A to C. So it means here, for the first one, the domain is A, and the or source is A, and the codomain or the target is B. For the second one, the domain is B, and the target is C, and codomain is C. And for the result, for the composition of two, the domain is A, and the target or codomain is C. So it's a binary operation, but it's not everywhere defined. It's defined only if the domain of one coincides with the codomain of another one. And then also the identity, but the identity is not the unique. It's unique for each object, and it's a homomorphism from X to X. And the composition, whenever it's defined of the identity, 1x with any other morphism is again the same morphisms, does not change. So it looks like the usual identity, but it depends on the point. All groups together with morphisms is a category with respect to the composition of morphisms. Indeed, so if we take C as all groups, objects of C, yeah, the same as all groups, homomorphisms from A to B as morphisms from one group to another one. It depends on the ordering, by the way, so we can order in a different way. And then the identity is the identity morphism which maps from G to G. So it's, in fact, it's what is called a subcategory of in the category of sets. Let me give more examples of groups, subgroups, and morphisms, and they are very important, and we'll meet them later in more elaborated lectures. So, for instance, if you take a vector space, real vector space with a scalar product, positive, or it can be also indefinite, but let's say it's positive, so it's Euclidean, what is called a Euclidean vector space. Then we can define the orthogonal group of V at the set of all invertible linear operators acting from V to V, which preserve the scalar product. So AV1, AV2 equals to V1, V2 for every V1, V2 from V capital. Now we can define in a similar way the unitary group. So instead of a real vector space V with a scalar product, we take a complex vector space with a Hermitian product or Hilbert product. So it means that the product is not symmetric, but it's cis-Q symmetric. So V1 with V2 equals to V2 with V1 conjugated, complex conjugated. Then we produce the same definition. We look at all A's in GLV such that AV1, AV2 equals to V1, V2, but now the round bracket is not the usual scalar product, Euclidean product, but the Hermitian product, and then we'll obtain the unitary group UV. Then there's a sequence of subgroups. SOV is a subgroup of S in SLV. You can require, so if you take an element OV, from the definition, it's easy to see that the determinant can be either 1 or -1. If we specify the determinant equals to 1, we obtain the special orthogonal group SOV inside SLV. And the same way, if you compute the determinant of any unitary element for finite dimension, of course, vector space, then you'll see that the determinant is a complex number with the absolute value equals to 1. If you specify that this is not just the absolute value equals to 1, but the whole determinant equals to 1, then this is the special unitary group SUV, which is subgroup is SLV. So if you consider the inclusion of a subgroup inside H, inside G, it's a monomorphism. So if you look at H itself as a group, then of course every point of H is inside G capital, and we can view this as a map which sends H from H capital to the same H but inside G capital, and this map is a monomorphism. So for that I used the special symbol for the inclusion for a monomorphism. The quotient map from G to G over H, so it means that we take an element in G capital and consider its class with respect to the equivalence relation introduced before in G capital over H for any normal subgroup H capital and G, and this is an epimorphism because every class in G capital over H comes from at least some representative. So it's a surjective map, means it's an epimorphism. Well, now we can relate everything to matrices, for instance, because matrices are very convenient to work with. So let's look at GLN over the field K, which consists of all matrices n cross n over the field whose entries are elements in the field K, such that the determinant of A is not 0. And you can see it's a subgroup. And now if you take any n-dimensional real vector space, any n-dimensional vector space over a field K, then one can find an isomorphism between GLNK and GLV. And we can do the same for SLN. So SLN K consists of all matrices n cross n, whose entries elements in K, the determinant of which is 1. And SLN K is isomorphic to SLV for any n-dimensional vector space over a field K. So in both cases, such an isomorphism is uniquely fixed by the choice of a basis. Whenever we choose a basis, then linear operator becomes a matrix. And this is precisely the isomorphism. The same for ONR, or similar procedure, or the orthogonal, the group of orthogonal matrices n cross n consists of all matrices n cross n over R, such that A composed with A transposed equals to the identity. And this ONR is isomorphic to OV for any Euclidean n-dimensional vector space. So a vector space with a positive n-dimensional vector space with a positive scalar product. And this isomorphism is uniquely determined by the choice of an orthogonal basis in V. Whenever we choose such a basis, then every orthogonal operator in this basis will give a matrix which satisfies the property A times A transponent equals to the identity. And apparently, obviously, ONR inside SLN-R, inside GLN-R are subgroups, which is very expected. Sorry, not correct. SO, it should be SO and R. Just spotted some mistake, because the determinant of ONR can be also -1. Well, let me give a few more examples. For instance, if we take Z integers, Q rational numbers, R real numbers, C complex numbers, any field K, any vector space V over any field K with respect to the sum, and these are abelian groups with respect to the sum, because the product will be defined for Z, Q, R, and C, but they will be not groups. Z inside R is a normal subgroup, because all structures are commutative and everything is normal. Whenever we have a subgroup of commutative group, it's always normal. If you consider the quotient of R by Z, it's S1, the group of rotations of the circle. The angle of rotation is parameterized by points of the circle, because the angle of rotation is actually some element between 0 and 2 pi, but 2 pi is the same as 0. So we should quotient mod out by integers. S1, the group of rotations of the circle, is isomorphic to the unitary group of a one-dimensional complex Hermitian space with the standard product. And this is the same as the set of complex numbers with the absolute value equals to 1. So the projection from R to RZ, if you represent S1 as follows, as above, as the set of unitary elements in C, then the projection map from R to R over Z is given by the following map. So we take a real A and then take the exponential of 2 pi IA, and this is an element in U1. So it's a complex number with the absolute value 1, but also the result does not depend on the choice representative. If we shift A by any integer, we obtain the same element in U1. Because this exponential is how it's written here, it's periodic. So one more example. If you consider integers, any integer p, even 0, but let's take it's not 0, and consider all elements of the form p times z, where z belongs to z both to integers, then pz is a subgroup inside Z, and of course it's a normal subgroup because everything is commutative. And the quotient is called the cyclic group of order P. You can see what are the number of elements. So it means that actually we divide an integer by P with some remainder, and this remainder, and this remainder will be from 0 to P minus 1. So the number of elements. And if it's P, we can already divide by P and will give 1. So it means, so the remainder will begin 0. So it means that the number of elements in ZP is, so the elements are parameterized by remainders 0, 1, 2, up to P minus 1. So the number of elements is P. And in particular, Z2 is isomorphic to the group we have seen before, which consists of 1 and -1, but now with respect to the multiplication of numbers. There is a more liberated example of groups, which is also very universal. It's called free groups. Let's take S a set with some elements. Let's take a set. We can always view, without losing of generality, in this course as a finite set, but it can be anything. Then the free group Fs over S, or generated by S, consists of all words that can be built from elements of S. So the elements of S then are called the alphabet. So we take every word, but then the two words, but not really every, because they're not all not the same, because otherwise we would get what is called magma, which is not our task. But here we require that two words are different unless the equality follows from the group axioms, and we'll see how it looks like. For instance, if you take S1, S2, S3 inverse, S2 inverse, S3, it's an independent word. We cannot make it easier how it's written here. But if you take S1, S2, S2 inverse, S3, S2 inverse is a formal element. It's just inverse of S2. We take elements of S, and to make it into a group, we also should invert them somehow. So S2 inverse is also an element in Fs. But now we know that by the group law, the group multiplication must be associative. So we can first multiply S2 with S2 inverse, and by the definition of the inverse, it's identity. So it's at S1 cross S3. It means that this word, which is on the left-hand side, can be short and simplified. So the word, word which consists of 4 letters is the same as the right-hand side, the word which consists of 2 letters. So Fs is universal. The free group generated by S is universal. So one can write what's the universality property. There's some factorial property, but I do not want to do it right now. It's not difficult to impose this condition. And it's unique up to an isomorphism. So if you have S and build a free group Fs, then 2 free groups will be isomorphic in a canonical way. Assume that all elements of a group G, now G is not the same as the free group, can be represented as a product of elements of some subset in G, maybe not in a unique way. So if, and they are inverse, of course. Then we can say that G is generated by S capital, means that all elements are words whose letters are elements of S. And then there exists a unique epimorphism from the free group generated by S to G, which sends these letters to the letters inside. So we have S inside G capital, which consists of all letters. And then we extend this map to all words built out of letters inside Fs, and then will be sent to the same expression inside G capital, and this will be an epimorphism of groups. So one can easily see that this map will satisfy the morphism property, and also it will be surjective as every element in G is some combination of products of elements in S and their inverses. And the kernel of this map from Fs to G capital consists of all relations. So in fact, in Fs, there are no relations other but the relations imposed by the group property. But inside G, there might be some relations. We'll see some examples of them. So it means that the group G is the quotient of the free group. If G is generated by some subset S, then G is the quotient of the free group generated by the same subset modular some relations. And we'll see examples. So another example of a group is the permutational symmetric group. And now I will repeat a few slides from the previous talk from yesterday. So permutations of, slightly modified, permutations of n elements, which we denote by Sn, is the group of bijections or automorphisms of the set, better to say, of the ordered set, 1, 2, and so on, n. So there are examples of permutations for n equals to 4. So one which I call tau, which sends 1 to 3, 2 to 2, 2 remains unchanged, 3 to 1, 4 to 4, 4 remains unchanged. And this is graphically represented below. And sigma sends 1 to 2, 2 to 4, 3 to 1, and 4 to 3. So there are no fixed points for sigma. To get the product of two permutations, we simply compose the corresponding isomorphisms of the ordered set. So first we perform tau. If we want to get sigma composed with tau, we first perform tau and then sigma. And then this will give you the result. Sigma composed with tau equals to another permutation, which sends 1 to 1, 2 to 4, 3 to 2, 4 to 3. But we can do this in the opposite order. So first perform sigma and then tau. And then the result will be tau composed with sigma 1 to 2, 2 to 4, 3 to 3, 4 to 1. And this is not the same as the product in the opposite direction. So it means that the group of permutations for the order 4 is not abelian. And the inverse, to find the inverse, we should simply invert the picture. So you see if sigma is like it's written on the left-hand side, that sigma inverse, we simply take the reflection of the picture with respect to some line, right? So if 1 goes to 2 for sigma, then 2 goes to 1 for sigma inverse, just inverted all arrows. So the number of elements in this Sn is the same as the number of permutations of different reorderings of elements from 1 to n, and this is the same as n factorial. Well, let me give you, it's another slide from the previous lecture. So, but I will repeat it now. So let's take a regular three-gon, so it's equilateral triangle, and consider all symmetries of this triangle. And this consists of rotations, which I take counterclockwise rotations, but we can also take clockwise rotation. So first is the rotation by 0 degrees. Which is the identity map because it does not do anything. Second, the rotation by 120 degrees. Third, the rotation by 240 degrees. And also the reflection symmetries, which are reflections or mirror symmetries with respect to some axis, which goes through one of the vertices. And this will be parameterized by the number of this vertex. Perpendicular, orthogonal to the opposite edge. So for instance, the first axis goes from 1 perpendicular to 2, 3, the second from 2 perpendicular to 1, 3, and the third one from 3 orthogonal and orthogonal to 1, 2, so the H1, 2. So the counterclockwise rotational symmetries gives us a abelian group. And in fact, you can see that this is the cyclic group of order 3. Right. So if you take, so let's look at the generator, which is the rotation by 120 degrees, the counterclockwise rotation by 120 degrees. The R square will be the rotation by 240 degrees, or clockwise 120. And in fact, it's the same as R square, and R times R square gives R cube, but this is already the identity. So this is the cyclic group of order 3. Now look at the mirror symmetries. So the mirror symmetry is parameterized by the vertices. So the axes are parameterized by the vertices. It's parameterized by the axis of symmetry, and they are parameterized by vertices. So let's denote this S1, S2, and 3. In literature, sometimes the notation is S0, S1, S2. But let me do this for the simplicity like that. And then you see that if you substitute this into the Cayley table, the table of multiplication, then we'll get either identities or powers, non-trivial powers of R, of the rotation. No reflection can be obtained from the product of two reflections. And now if you write the whole table of symmetries for the equilateral triangle, we'll obtain the following one. And it's easy to see that this is not commutative. For instance, if we take the product of R and S1, it means that R is the row, S1 is the column, we'll get S3. if we do the same with S1 and R, we'll get S2, and S2 is not the same as S3. They are reflections with respect to two different axes. So it means that the product of the group of symmetries of the regular three-gon is not abelian. So the product, the result of the multiplication depends on the choice on the choice of the order. And now this table looks pretty nice because we already seen this group and we can easily recognize what it is. So the group of symmetries for the equilateral triangle is isomorphic to S3, to the group of permutations of three elements. And in fact, it's easy to see why, because every symmetry will somehow exchange the vertices, right? So for instance, this symmetry 1, 3 exchange between 2 and 3. The second one, which is in the middle between 3 and 1, and the third one between 2 and 1. So, and in the first one, 1 is remains unchanged, the second one 2, and the third one 3 is a fixed vertex. So in effect, it means that this should be a subgroup inside the group of permutations of all vertices. And this is indeed true, but in the case of the regular triangle, this is just the whole group of symmetries, the whole symmetric group. And the correspondence is easy. The identity is sent to the identity. So it's the neutral element, which does not change 1, 2, 3. R is the cyclic rotation, which sends 1 to 3, 2 to 1, 3 to 2. R should be R square, sorry. R square is another cyclic rotation, which sends 1 to 2, 2 to 3, 3 to 1. S1 is a flip, which sends 1 to 1, but exchange between 2 and 3, and so on. If you just write this correspondence, you'll obtain a map from the group of symmetries of a regular triangle to S3, and this map is actually an isomorphism of groups. It's a morphism of groups, and it's a bijection. In general, a dihedral group, or the hedral group, is the group of symmetries of a regular polygon, Dn for the n-gon. So before we had n equals to 3. For 2, actually, it's just a segment of a line with 2 points. And it's easy to see that this will be, all symmetries will consist of the identity and the reflection, which exchange between 1 and 2 vertices. And this will be also S2. So in these two cases, for n equals to 1 and n equals to 2 and n equals to 3, they obtain the whole symmetric group. But in general, it's not the case. In general, it's a strict subgroup. It means it does not coincide with the whole group. And one can also see how it looks like. So we can enumerate all possible generators. This will be again rotations and reflections. And in fact, the Cayley table is also pretty simple. One can compute it. Not as simple as for the triangle, but it's quite simple. I remember that I tried to talk about the braid group in the previous lecture, but it was too popular. I also forgot some detail. And let me repeat in a more sophisticated way today. So there's another example of groups, which is called braid groups. So a braid groups of n strands, we can also call them strands. We can call them in a different way, threads, for instance, or strings. This will give the same. And this is denoted by Bn. Also, it's known as an Artin braid group. This is the group whose elements are equivalence classes on n braids with respect to some sort of isotopy. So but it's easier to see rather than to explain, easy to show rather than to explain how it's defined. Whose group operation is the composition of braids. So this is the example of 2 braids for n equals to 3. So I color it the threads or strands by colors red, blue, and green. And you see that one thread in this graphical description, one strand either goes over the another one or under the another one. So in fact, if you connect the opposite sides, we will get a knot. And this is one of the ways how to describe knots in 3-dimensional space by use of the braid group. But I will not talk about this now. It's one of the nice descriptions. And this is another one. You see that they are different between, for instance, in the left-hand side and right-hand side, red and blue have the same position with respect to each other, but the green is not, right? Because in the first picture, green goes over red one, and the second one under the red one. So they're two different braids. So how to multiply two braids? So we take one, another one, and then just compose, right? We combine the ends of the first one with the of one with the beginning, with the starting points of the second one. We'll get another braid. So in fact, it's easy to see that the group will consist of infinitely many possibilities. So it's infinite group, but still discrete, but it's an infinite group, because we assume that there are infinitely many possibilities of the nodes. So there are many different ways of two strands go either over or under. So you see before it there were only 3 nodes, but now there are more, right? 1, 2, 3, 4, 5, 6, right? 3 plus 3. For the inverse element, we do the same as for the inverse element in the symmetric group. We should simply reflect our braid and compose again. Okay, let me do this how it's written here. We take the left hand side, then reflect it. We obtain the one in the middle. You see this just the reflection with respect to the horizontal symmetric line. And then we compose them and we obtain something which looks non-trivial. But in fact, it's not, because now we will do the isotopy, right? We take the one which was on the right-hand side. I just copied this. And then pull out by the ends, beginning and ending of the threads, and we'll obtain three straight lines. So right, they should be somehow longer, right? But let's assume that they are the same length, but it doesn't matter anyway. So if we pull out, or do the isotopy, precisely the isotopy procedure in topology, we'll obtain 3 lines, and this is the identity or neutral element in the braid group. It's not always possible. If you do this for some non-trivial braid, we will not get 3 lines. This will be some wrapping or something of that sort. So let me show the generators. So in fact, this group is infinite, but it's finitely generated. There's a finite number of generators. And let me show the generators for B4, for the braid group of order 4. So this is the neutral element, of course, which consists of 4 straight lines. I colored them for the simplicity. The first, sigma 1, and this is the red one goes over the blue one. Sigma 2, the blue one goes over the green one, and the 2 others are straight. And for the third one, sigma 3, green goes over the purple. If you do this in a different direction, so if red goes, for instance, under the blue one, this will be C1 inverse. But as already said, for them, if the group is generated by some set S, we consider not only products of elements in this set, but also the inverses. So sigma 1 inverse is supposed to be one of the elements. For instance, you see, but just remember that for the symmetry group, for the group of permutation, the product of 2 flips, we just exchange 2 elements, is the identity. But if you take sigma 1 and again sigma 1, 2 copies of sigma 1, and take the product, it will be not the identity. You see, if you pull out by the ends, we will not get 2 straight lines anymore, right? It's already wrapped. But if you take sigma 1 and sigma 1 inverse, so for sigma 1, red goes over blue one, and for sigma 1 inverse, blue goes over the red one, compose them and pull out, we'll get 2 straight lines. So this is the neutral element, which means that sigma 1 inverse written as on the picture, it's indeed the inverse element with respect to multiplication in the braid group. So let me show the example for B3. So there's a morphism of groups from Bn to the symmetric group of the same order. And you see that for any braid, we take the starting point which are colored by red, blue, and green, and obtain the ending points, which again colored by green, blue, and red, but they're different orders. So it means that for in this case, 1, 2, 3 goes to 3, 2, 1. And this produces some permutation. Obviously, we can produce any permutation. So this map from Bn to Sn is surjective. And second, how we multiply two braids, it's obvious this also morphism of groups. But this morphism is not an isomorphism. Moreover, the kernel is infinite, not infinite dimensional, but infinite. Sorry, yeah. So it's not an epimorphism. Sorry, it's an epimorphism, but it's not a monomorphism. So for instance, if we take one braid, which is yeah, so okay. Yeah, sorry. So it means that we can do two braids, which are sigma 1 and sigma 1 inverse in the previous notations, and both will cover the flip, the permutation of 1 and 2. But they are different. And for instance, instead of sigma 1 and sigma 1 inverse, we can take a more complicated one, right? And this will still cover 1, 2, 2, 1, right? So there's can be infinitely many nodes, infinitely many possibilities to cover the same element in this case in S2. So the kernel of this map, which is, as we know, should be a normal subgroup, the kernel of the morphism, epimorphism from Bn to Sn is called the pure braid group, and this is denoted as PBN or Pn, and this consists of more than one element and even infinitely many elements. You can see that, for instance, for n equals to 2, the n will be just the cyclic group. Sorry, it will be just that, because it will count how many times you wrap one over another one. So there are generators, sigma 1 and so on, sigma n minus 1, as we have seen before. And then they are subject to the relations. Well, they're pretty nice relations. Sigma I plus 1, sigma I equals to sigma I plus 1, sigma I plus 1 for all I between 1 and n minus 2. N minus 1 already not, does not fit. So, and then sigma I, sigma j equals to sigma j if I and j are sufficiently far away from each other. Now let us look at the symmetric group. And in the case of the symmetric group, we have also generated sigma I, which are the permutations between I and I plus 1, or the simple flips. And then this set of permutations or transpositions, Jasmine transpositions, will generate the whole symmetric group. And this will be subject to the following relations. So the two relations, sigma I plus 1, sigma I equals to sigma I plus 1, sigma I plus 1, and sigma I j equals to sigma j, sigma I for sufficiently distinct I and j. These are the same as for the braid group. But the first one, sigma I squares to 1, which is the property of the transposition. Every transposition squares to 1. And this is not present in the set of relations for Bn. It means that in fact it is what we expect to be, right? If we have a map, a surjective map or epimorphism from one group to another one, the first group is generated by some elements, the set group is generated by another elements, and the morphism sends the first set of elements to another set of elements. Then the generators in the target should be richer, should be more relations. So they're the same relations for the braid group, but one additional. And this additional relation will generate the quotient of the map from Bn to Sn. Now let me, since we actually had the geometry school, let me give some relation to the algebraic topology. So Bn is isomorphic to the fundamental group pi1 of the configuration space of n points on a disk. And the free group Fn is, which is generated by n elements, is isomorphic to the fundamental group of the n punctured disk. So let me show the pictures. So what is the first one? So the configuration space of n points on a disk. We take disk, we consider n distinct points. In this case, these are 1, 2, 3, 4, 5, 6, right? And then we try to change the positions of these points such that they will remain distinct. They will not coincide. And this is what is called the configuration space. And let's look at the pi1, the fundamental group of this configuration space. And this fundamental group will be, in fact, it depends. So we should, I think if I remember correctly, we should parameterize by the symmetry group. Then it will be Bn or the pure Bn. So this also depends. So in this case, we should also somehow do not count the order of the points. And if you change the position, then all paths up to the homotopy, all places starting and ending at the same point up to the homotopy in this configuration space with respect to the concatenation will be what is called the fundamental group P1 of the configuration space, will be isomorphic to either Bn or Pn, depending on whether we take the quotient by the symmetric group or not. And for the free group, we take the disk with n points being extracted and consider the fundamental group of this. And this will be generated by cycles. You see every cycle wraps one of the points, and there are n cycles. And the relations in the fundamental group between these cycles is free. There are no relations, except it's a group. Now I'm coming to the end, so I'm slowly moving to the representations, which is the subject of the lectures. So if you have a group and a set, we say that G is acting on X, or also G is called X is called the G space, if there exists a binary operation whose elements are elements on G on the left-hand side and X on the right-hand side, so it sends a pair GX to GX, and which satisfies the associativity in such a way that G1 applied to G2X is the same as first decomposition of G1, G2, second applied to X for all elements G1, G2 in J capital and X in X capital. But also there is a neutral element in G, and this must act as the identity. So the neutral element applied to any element X in X capital gives the same X. As a corollary of the above properties, if we fix G in G capital and consider the following map, which sends X small in the X capital to GX, this must be a bijection because sorry. No, I have to specify that the okay, not really. Yes, I'm sorry. Yes, it's a bijection because if you take G and G inverse, then G inverse composed with G gives the neutral element. It's the identity. Yes, it's sufficient. Equivalent, we can say in equivalent way that there is a morphism of groups from G capital to the automorphism or symmetry group of X, which sends G to the above map X, the above map G determined by G sends X to GX. So automorphism X consists of all bijections. An action is called free if for any X in X capital from the property GX equals to X, we immediately obtain that G is the neutral element. So there are fixed points only for neutral elements. An action is called transitive if element of G can relate in the above way any two elements in X capital. So for any X small and Y small in the X capital, there exists G in G capital such that G small applied to X gives Y. And in such a case, X is called a homogeneous space. If an action is free and transitive, then X capital is called a principal G space or a G torso. So in fact, as we have seen before, G torso is the same as G itself, except we forget about the position of the neutral element. So G without neutral element, the neutral element being forgotten is G torso. Okay, let me give a few examples of group actions. First of all, the automorphism is X is acting on X. right? Because elements on automorphism of X or the symmetry group of X consist of bijections, and they're easily acting as they should act. Any subgroup of automorphism of X is acting on X. This action is induced by the natural action, canonical action of automorphism X capital on X. Let's consider left multiplication of G on itself. So let's take the multiplication, which is a map G cross G to G. And the right copy of G is viewed as X capital, and the left copy is G, is still G. This action is free and transitive, so G is a G tensor over itself. If you take the right multiplication, say G, first G is X, and the second copy of G is G, this will be no more an action. So it's an action up to reordering, unless G is a commutative group. Instead of G capital, we can take any subgroup H of G capital, and this will be an action. And this action is action of H in G. This will be free, but no more transitive. Consider an action of the group of invertible linear transformations on V in a natural way. So there's an action by linear transformations, and this is again an action. But this action preserves the structure on V, the structure of a vector space. So it's a very particular kind of action, and we'll be interested in these kind of actions. So an action of G on a vector space V capital by linear transformation is called a representation of G on V. And then V is called a G module. Representations of G on V are in one-to-one correspondence with group morphisms from G capital to GLV. Right before we have seen that actions, just in the previous slide, we have seen that an action just in the middle of the slide, a morphism, an action of G on X is the same as a morphism from G to automorphisms of X, to the group of bijections of S, right? Because every element G in G capital corresponds now to some bijection of X capital, and this gives a group. So the properties, the above property gives the properties of a morphism. And for the representation, the same, but instead of automorphisms of V, we must consider all linear invertible maps, all linear bijections. This is GLV. Okay, so now it's the time to stop. So I'm stopping with the words representation, and I will start with this in the next lecture. So that complexity will increase from lecture to lecture. So today it's should be accessible for all students, of course, and the next lecture will be more complicated, but still, I guess, I hope accessible either. So thank you. So the presentation file will be online, I guess, from tomorrow or something, as soon as I will fix all the mistakes. So should I say goodbye or what? Okay. So there are no questions, right? If I understand correctly. So I see many. Thank you, but there are no questions. Oh, someone has a question. I think Anton has left, right? So a question of the logistics of the summer school. Okay, it's not to me. So others are just things. Okay. So then I should probably stop recording and